Hello everyone. The topic that I want to talk about is downscaling metal oxide semiconductor field effect transistors or MOSFETs and its effect on current voltage characteristics. First, let's see why downscaling is important. There are both technological and economic advantages in reducing the dimensions of transistors and cramming more and more into a chip. The first one is performance improvement. Smaller MOSFETs typically exhibit faster switching speeds and lower power consumption compared to their larger counterparts. This is due to reduced parasitic capacitances and resistances, leading to improved performance in electronic devices such as computers, smartphones, tablets, and etc. The second is increased integration density. Downscaling allows for packing more transistors into a given area of a semiconductor chip. This increased integration density enables the development of more complex and powerful integrated circuits, facilitating the creation of advanced technologies like high-performance processors, memory chips, and sensors. Cost reduction. As the size of MOSFETs decreases, more devices can be fabricated on a single semiconductor wafer, leading to economies of scale and reduced manufacturing costs per transistor. This cost reduction can translate into more affordable electronic products for consumers and increased profitability for semiconductor manufacturers. And the fourth one is energy efficiency. Smaller MOSFETs typically require lower operating voltages and consume less power, making them more energy efficient. This is particularly important in battery-powered devices, where energy efficiency directly impacts battery life and overall device runtime. Now that we understand the importance of downscaling transistors, let's see how downscaling works. The following is one of the most important research works in chip designing. The research paper titled Design of Ion-Implanted MOSFETs with very small physical dimensions, published in 1974. At the time, available high-resolution lithographic techniques allowed chip designers to decrease the dimensions of the transistors. But as we can imagine, changing the dimensions of a transistor can cause some problems. One of them is short channel effect, which happens when we reduce the length of the channel L here in figure 1a, and we don't touch other dimensions such as the length, the width of the channel here, which causes a reduction in the gate threshold voltage at which the device turns on. Another thing is the substrate sensitivity, which is an important criterion in digital switching circuits, because the design becomes difficult if the threshold voltage increases by more than a factor of 2 over the full range of variation of the source voltage. So in designing a transistor, we should always make sure that we choose dimensions that give us the best possible substrate sensitivity for our purposes. The authors of the paper offered the following changes and transformations necessary in downscaling the transistors. It's transformation in 3 variables. First, the dimension. All linear dimensions are reduced by a unitless scaling factor k. It means that we are changing all of these dimensions, the width, the length, and also the uh, oxide thickness with the same scaling factor. Like in this example here, the scaling factor is 5 because we are reducing the length of the channel from 5 microns to 1 micron. And the same scaling factor is also applied to the width of the channel and also the oxide thickness. Second is the voltage. The voltages applied to the device are also reduced by the same factor. And the third is doping. The substrate doping concentration is increased again using the same scaling factor. Next, with scaling the dimensions, voltages, and also doping the substrate, we can find the following scaling relationships. Depletion layer width, using this relationship here, can be shown that also reduces by the factor K. Gate threshold voltage also approximately reduces by factor K, and the MOSFET current also reduces by the same factor K. Actually, there is a scaling results table that the paper suggests, and we can see that the device dimensions are scaled down by the factor K. The doping concentration of the substrate is increased by factor K. Voltage, current, capacitance, and delay time are all reduced by factor K. The power density remains unchanged, and the power dissipation is reduced by factor K squared, which is very interesting because the power dissipation is very important factor in chip design. We always try to minimize power dissipation in electronic devices and the chips. Therefore, by scaling down, we can minimize the power dissipation by the factor of K squared. Authors of the paper also conducted an experiment to verify the results. Two sets of experimental devices were fabricated with gate insulators or the gate oxide thickness of 1000 and 200 angstrom. In other words, the scaling factor is 5. One of the devices has 1000 angstrom gate insulator, and the other one has 200 angstrom. After gathering all the data from the experiment, as we can see here in figure 2, the drain current versus drain voltage graph for both devices are approximately the same. And the voltages are exactly scaled down by the factor of 5. 20 volt here, and we have 4 volt here. 15, and we have 3. 10, and we have 2, 5, and we have 1 here. All of them scale down by the factor of 5 as we scale down the gate oxide thickness. And also the channel length is also scaled down by factor of 5, which the results verify the mathematical conclusion that we already saw in the previous slide. The other relation between the MOSFET current and the gate voltage shows that the gate threshold voltage, as we can see here, is also scaled down by a factor of 5. Here we have 0.44 volts, and with the larger device we had 2.10 volt. As we can see in the smaller MOSFET, we have the gate threshold voltage scaled down approximately by a factor of 5. The only thing that is not following the scale as desired is the subthreshold behavior. Here, if we see the graphs below the threshold voltage, these two are identical, and therefore we conclude that only in subthreshold voltages we do not have the scaling as we wanted. Therefore, the designers should only just take it into account in their designs that for this region the scaling does not work, and for all the other purposes the scaling is following the trend. In the scaled down transistor, the thickness of the oxide layer is very, very small, 200 angstrom, or in other words 20 nanometers. And it is very difficult to manufacture a transistor reliably with such dimensions. Therefore, the authors introduced a technique that enables designers to increase the thickness of the oxide layer and solve the problem for the manufacturing of the transistors reliably. The technique is called ion implantation, increasing gate insulator thickness made possible by ion implantation technique. And it is done by lowering the initial substrate doping. So the substrate that we have in here has less concentration compared to the previous scaled down transistor, and heavier doping of the region within the surface depletion layer by implanting boron surface layer. More concentration in the depletion region, between the drain and source and under the gate here. And also reducing the dimension of the junctions, the shallower junctions, to avoid loss of threshold control. And such a design has another advantage as well. It has a smaller capacitance of the device due to wider depletion layers. So the authors continue with more details with the ion implantation technique that will be the topic of another presentation. So I will stop here, and I hope that the information given here was helpful about the downscaling of the MOSFETs.